Okay, let's tackle a composite system here. So this is a system of a converging lens, and we're given the focal length of that lens, and then the spherical mirror. So this is going to be a convex mirror that's shown in the diagram. And we can also know it's a convex mirror if you look at the focal length that's given, negative 5x. So negative focal length indicates that that would be a convex mirror. Okay, so you should have those signs, the signs of the different types of mirrors and lenses, um, kind of have those committed to memory. It'll just make it easier as you're working with them. And there are really only two kinds of lenses that you need to know about, right? Converging and diverging lenses, and then two types of spherical mirrors, convex and concave. All right, so how I like to do this is just kind of follow the light and go in order of what the light does. So as the light leaves the object, right, as the light leaves the object, it's going to go towards the lens. So let's just look at when the light interacts with the lens. And this will be, it's going to go through the lens twice if you look at the problem that is given to us here, but we're going to just focus on the first time. So it goes through the lens two times. So I'm going to actually label that. I'm going to say right now my work here is going through the lens the first time. And I think it's really useful to keep your work organized because you have to solve these problems in stages. So it's useful for me to have a look at the direction of light. So the light direction is going to be to the right. I'm just going to indicate that with an arrow there. So light is moving to the right. That matters because that's going to have an impact on our signs when we look at signs for object and image distance. So cool. All right. So what's my object distance here? I can kind of think about that first. So I'm going to use P as my object distance, Q as image distance. So my object distance is obviously 10x. That's given in the problem. And then for my image distance, I'm going to use the general equation. Now, let me just remind you of the general equation. 1 over F is equal to 1 over P plus 1 over Q. I'm sure that we're fairly familiar with this by now. And also that I often encourage students to don't just like sub values into this general equation in the form it's given, but solve for the thing that you're interested in, algebraically isolate that first. So for instance, if I'm interested in image distance, which I often am, and I solve for that from the general equation, what I get is product of focal length and object distance over P minus F. It's useful to have it in that form before moving on. So those are what I'm going to put those up here because those are kind of my general forms there that I'll use. So Q is equal to, now I have my focal length. I'll just kind of um, write this out here first just so that we can follow along. Focal length times P over P minus F. Now let's sub into that. So the focal length for this lens is a positive 8x. The object distance is positive 10x. It's positive because the object is on the side of the incoming light. And then that's over P minus F. So that's going to be over 10x minus 8x. This gives us 40x. Right. I notice that this is positive. Okay, so this 40x is positive, which means that it is located to the right of the lens. And what that's about, remember, when it comes to our sign rules here, is that the image distance is positive when it's on the side of the outgoing light. For this lens, the outgoing light is on the right side. So this image we expect to be 40x to the right of the lens. If you look at the diagram, 40x would be off the page, really to the right. So it's way, way behind the mirror. Kind of always, I think it's a really good idea to keep in mind where these intermediate images are. Okay, even if no one's asking you to draw it on a diagram, to have that conceptually in your mind. Okay, great. Now let's look at the mirror. So we've gone through the lens, and now the next component that we hit when we're doing this problem is the mirror. Cool. So for the mirror, now we need to find what is the object distance for the mirror. So I'll just prime this. So for the mirror, now think about it. My object is, or the image from the first. I'm just going to try to kind of put that little interruption there, and I'll put a little X right here, say where that, and how I label this is I call this image 1, the very first image that's formed by the system. And if that's 40x to the right of the lens, what that means is that it is 30x behind the mirror, right? This distance would be 30x. Okay. So, however, because it is not on the side of the incoming light, that's a negative object distance. So this object distance is going to be negative 30x. So that's what I mean about like having an idea of physically where it is, because that's the only way that you can judge the correct sign for the next object. So the image from the first component, the image from the lens, that constitutes the object for the next component. And you can go on and on that way as we will, right? So that means image 1, the image created by the lens, that's now the object for my mirror. And because it's located behind the mirror, it's not on the side of the incoming light. So the object distance is negative. And sometimes we call that a virtual object. All right, now let's find our second image, which is the image that's created by the mirror. And that's just going to be, we're using the same equation there. So I'm going to use the mirror focal length, which is negative 5x, multiplied by the image distance, which is negative 30x, all over negative 30x minus negative 5x. Use parentheses here, right? You don't want to just drop signs or do the sign math in your head or whatever. Be really clear, especially when you first write out your quantities, and then take a moment, like make it one of the steps that you do to deal with those quantities. So I see that here in the numerator, I'm going to have positive 150x squared, and in the denominator, negative 25x, and that leaves me with negative 6x. So notice that we have now a negative image distance. So that means that it is not on the side of the outgoing light. Now for a mirror, let me pause just for a second. Mirrors and lenses are different, right? For a mirror, you have both the incoming light and the outgoing light on the left side of the mirror in this problem. The incoming and outgoing light are on the same side of the mirror, obviously, right? There's the other side of the mirror, this is the dark side. When it comes to lenses, it's not that way. Since the light goes through the lens, the incoming light is on one side, the outgoing light is on the other side of the lens. So, but right now we're talking about the mirror. So this negative image here, image distance, that means that the image is not on the side of the outgoing light. That puts this image to the right of the mirror, a distance 6x. So I would put my image 2, like I could put it like, say, right here. I'll call that image 2. And then this distance here would be 6x. Okay. Good. So again, that maybe helps you kind of stay in touch with what's going on in the problem itself. So this is going to be here what we often call behind the mirror. So you could say to the right of the mirror too, but behind the mirror just makes it really clear that we're not on the shiny side of the mirror. Okay, good. So now we've bounced, we've gone through the mirror, we've used the mirror, basically, we say it that way. And now we're looking at image 2. Image 2 is now the object for the lens going through the lens the second time, right? And if you're following this, you see that we could like keep doing this forever, really. We could keep finding images and applying them to components. And that's one of the reasons for being really clear in the problem that I'm interested in the light that's gone through the lens exactly twice. All right, so now let's go and work on the lens the second time here. So we're going to look at the lens again. different object, of course. Second time. Okay. And now my light direction is right to left. I'm just going to go back real quick to the diagram. So now that I'm going through the lens the second time, I'm coming back because now look where my object is. I2 is my object now for going through the lens the second time. So now I'm considering light that's going through the lens this way, right? So my incoming light is on the right of the lens now. My outgoing light is now on the left of the lens. Okay, so we need to figure out what is our object distance here. I'll just use a double prime. Let's go back to our diagram. What's our object distance? Well, it's 10x plus 16x, and it's on the side of the incoming light. So it's, 10x plus 6x, which makes 16x, and it is on the side of the incoming light. So it will be positive. So that object distance will be a positive 16x. Now I can solve for my image distance. That will just be my 8x, that's my focal length, times 16x over 16x minus 8x. That gives me 16x. That's positive, so go back, look at our diagram. If it's positive, that means it's to the left of the lens, right? It's on the side of the outgoing light. So my final image is like here-ish, right? I'll call that I3. It's my final image. And it's so it's 16x from the lens. That means it's 6x. That dimension there from the object, right, is 6x. So there's my final image. Cool. So this 16x is to the left of the lens. So notice that I keep describing, instead of just putting down an image distance, next to that I'm really clear about like exactly where that is. What I see sometimes when students just kind of speed through these problems and treat them basically like algebra problems and don't connect conceptually, I see two things. One is a lot of sign errors because they're not thinking about what direction the light is going and where the different objects are. And the other thing I see is not really understanding how to interpret these image distances. So just because you have an image distance doesn't mean that you understand the position. You with me here? So if I tell you the image distance is 8x, or someone calculates that for me or whatever, I still want them to tell me, where is that, right? If that's your image distance, all that does is give you a distance from the component. Can you tell me where that is in the overall physical scenario? So that's really important to be able to put that stuff together conceptually. Obviously, the math when it comes to these problems isn't super, involved. Okay, so this is my final image actually right here, right? So this is my final image for light that's gone through twice. The question asks us some other things about the final image, so let's figure those out. Because my image distance, the very last image distance is positive, my final image is real. So let's describe the image. It's a real image, and that's because Q double prime is positive. Now, it doesn't matter if any of the intermediate images were virtual. It doesn't matter. You just look at the last image distance, the final image distance. You look at that one, and if that one is greater than 0, then you know that you have a real image there. Okay, so now let's figure out the magnifications, because that's part of describing my final image. And I'm going to do these one at a time. So I'll just do 1, 2, and 3. The magnification 1, that's the magnification that occurs going through the lens the first time, right? And this is always going to be negative Q over P for every one of these. And remember that that negative sign is in the equation. So if I look at that for my very first one, just go back here. I see that Q is 40x and P is 10x. right? So that'll be negative 40x over 10x, and that gives me negative 4. Let's figure out the next one. Magnification 2, again, that's negative q over p. We could say this is actually q prime over p prime, right? To stick with our notation. And if we look at what those two are, that's going to be negative 6x and negative 30x. So negative 6x, remember, don't just ignore those signs, over negative 30x. And that gives me negative 1/5. That's supposed to be a 5. And then my third magnification here is going to be negative q double prime over p double prime. And that will be negative 16x over 16x, which just gives me negative 1. So let's look at the effects of these one at a time just to discuss them real quick. So this M1, what it does, right, if I look at this magnification of negative 4, I know that it's inverted and it's magnified by 4 times, right? If I look at the second one, it's negative, so it's again inverted and it's diminished, smaller. And negative 1 here, this last one, it's again inverted and there's no change because it is that it's just equal to 1. It's neither greater than or less than 1. So my final magnification, then we can call this the total magnification, is the product of your individual magnifications. And I'm going to let you think about if you're surprised, like, why is it the product? That's something worth spending a little time on to try to get a conceptual feeling for that. So product here is going to be negative 4 times negative 1/5 times negative 1. That gives me negative 4/5 for my final image here. So this is my overall magnification. This is what my final image will look like. So I can see that my final image is going to be inverted and it's going to be diminished by 4/5. Okay, so we've described the final image. Basically, we want to know where it is, and you can locate it different ways, but the way that we located it here is we said it's 16x to the left of the lens. That's an unambiguous way to locate the final image. And then what we've said about the final image is that it's real, it's inverted, and it's diminished by 4/5.